Mm, Hello. So today we are doing reading material 1 from the course Physics of Soft Condensed Matter. I am Nishant Sachdeva and my roll number is 2018111040. In this reading material, we will be dealing with correlation functions and some other related mathematics before we hop onto the harmonic oscillators. That's what we'll study towards the end of the paper. Now, correlation functions, what are they? So we see that the time dependence of both classical and quantum mechanical dynamic variables is basically governed, or let's say determined, by the Hamiltonian. Now, how does that link to us? It's basically that any quantum mechanical operator, it evolves in time in the Heisenberg representation according to the formula given right here. And you can see the Hamiltonian being present over here. So that's how we see the correlation of the Hamiltonian with the quantum mechanical dynamic operators. Now, we will often be looking at the frequency rather than the time dependence of these operators. And now, when we think of frequency, normally what comes to our mind is the Fourier functions. That's what these are. We will be converting the time operators into the frequency variable and back and forth. We will frequently take a look at these time dependent correlation, and the variables will be normally like a distance or say, let's say density, one of those. Now, apparently we studied static correlations in these particular sections before coming here, before this paper started. So now we will take a look at these time dependent correlation functions, and we can see that they can be made with the same analogy as the static correlations. So these are two are what we end up with. Now we have to like, okay, so what it mentions here is that in the static case, this particular operator signified the average with respect to an equilibrium ensemble, with respect to an equilibrium ensemble. Now, because the time evolution of these particular fields is governed by the Hamiltonian according to this equation right here, there is no ambiguity in the meaning of these averages. For each value t and t dash, they basically are calculated by tracing over all points in the phase space, or if you're dealing with quantum operators, then quantum states weighed by the appropriate equilibrium weight function. So when t becomes the same as t dash, these correlation functions collapse, or let's say reduce, to the static correlation functions that we got from chapter 3. Now, what they are basically saying is that these formulas, when dealt with in the Hamiltonian and the different time frames, give us these two. And when in these upper two, we put the same t as t dash, we end up with these two functions. Now, unless it's specified otherwise in this paper, we will only consider Hamiltonians that are independent of time. Now, why we do this? Because we want the thermodynamic averages of various quantities that we're going to get, because we are studying harmonic oscillators later on. So whatever thermodynamic averages we're going to get, we want them to be invariant under time translations. Okay, so now we realize that, okay, as we calculate ahead, we get the correlation functions C phi I phi j and S phi I phi j, and we want them to depend only on the difference t minus t dash. Now this got hidden under my thing, so I'll erase it a bit. So we want the functions to be dependent only on the time difference rather than the actual values. So the correlation functions then of these temporal Fourier transform variables can then be transformed and written as these particular two. The correlation function that we get here, which is C phi I phi j of x, x and omega, we often call it the power spectrum of phi I with the for given x and t. These two equations basically can be called as the generalizations of the Wiener-Kirchner theorem. This doesn't highlight, so I'll just underline it, but it's called the Wiener-Kirchner theorem. This relates a power spectrum to the Fourier transform of a time-dependent correlation function. I'll repeat that again. It relates a power spectrum to the Fourier transform of a time-dependent correlation function. Keep note of how we are talking about time dependence and eventually wanting to not depend on time. Similarly, now we define in the same format as equation above, similar equation but with different variables for different functions. So S phi I phi j is an integral over the time differences going from minus infinity to infinity. So from this above equation, then from here, putting it into this one, we get this particular answer. So there we are able to relate this quantity and this quantity with each other. Now this here equation that we get, in this equation, this part contributes only to the zero frequency or static part of C phi I phi j. These variables or operators contribute only to the zero frequency or static part of C phi I phi j. We will move on now to the response function. So far we've only done correlation functions. Now we shall move on to response functions. Okay, so now just as the static susceptibilities, they relate changes delta in averages of fields. What do static susceptibilities do? They relate changes in the averages of fields to changes in the external fields which are conjugate to phi j of x. What's phi j of x? The dynamic response function. Relates changes delta average of phi I for a given x and t in averages of time dependent fields to time dependent changes delta hg for a given x dash and t dash in external fields. We shall read this again for more clarity. So what we arrive at is that, now we'll read this again for more clarity because this is a bit complex and we'll acquire this so that we can understand how the functions happen ahead. So just as the static susceptibilities relate changes in averages of fields to external fields conjugate to phi jx, similar to this operation, the dynamic response function relates changes in averages of time-dependent fields to time-dependent changes in the external fields. What's happening here is that there is something called static susceptibility. It relates changes in the averages of fields to change in the external fields which are conjugate to phi j of x. In a similar fashion, the dynamic response function relates changes in averages of time-dependent fields to time-dependent changes in the external fields. Now, it is very important to recognize the difference between temporal and spatial variables in this equation. Temporal and spatial, they sound similar with temporal and space, but they are a slight difference there. We'll see that. Disturbances at x dash can lead to changes in phi I for a given x and t's average at all points x, which is okay, which we understand. Now, disturbances at the time t dash can lead to changes only for times t which are later than t dash. So we have to say that, okay? When a change happens in x dash, it really leads to changes at all points x. Now this is hidden by a thumb, but we can see it later on, or maybe in the next page or something. But disturbances at time t dash can lead to changes only for time t dash, which is bigger than t, which means which are for operations that are happening later than the time t. So that means the responses of these two functions are causal. Now this is again hidden by the thumb, so we'll go ahead for a bit. If we need to come back, we'll do that. That's fine. So great. So what happened was there was this thumb thing here. So now we're coming back and we can actually see what's happening here. This is actually the same page here. These two are the same pages, so we'll just go ahead. Now what we saw was that disturbances at time t can lead to changes only for times t later than t dash. So the response functions here are actually causal. They depend on the previous values, and if there's any change in the previous values, they will change. For the x part, any change at x dash could affect all the x around it. So that's a basic difference here. This means that the response function x tilde phi I phi j can be non-zero only for t bigger than t dash. It is very useful to incorporate this step function dependence. It is very useful to incorporate this step function dependence on time into the definition of the response function. Be careful what we're wording here. They are incorporating the step function dependence on time. This thing can be non-zero only for t bigger than t dash. There's a dependence there. We need t to be bigger than t dash. How we use it? We incorporate this particular dependence on time into the definition of the response function. What was the response function? It was up there. So we inculcate that into the response function by writing this particular equation, where eta of t minus t dash can be 1 only if t bigger than t dash and 0 only if t less than t dash. Now Be careful here, okay? This particular guy over here can be non-zero only for t bigger than t dash. That's exactly what's happening here. So for t less than t dash, it's 0, and we keep it as 1. So we basically make sort of a step function thing. Now this particular thing is called the Heaviside unit step function. Heaviside unit step function. The factor of 2 iota. Iota is a complex number which is called the square root of -1. That factor is basically at this stage arbitrary. There's no particular reason to have it. It's only mathematical, it's empirical. But it will make our comparisons, I'll again rub this because I've made a mark here. It will make our comparisons with our later, more formal development more straightforward. Basically, this is a mathematical convenience. We will be dealing with equations which are far more complex than this particular one. And we will need to have some mathematical factors which make our work easier. So that's basically what we're doing here. Now, equation 7.1.12, which is this particular guy here, it can be viewed as a definition of x tilde double dash, which is the double derivative of x tilde for a phi I phi j, which is basically purely imaginary if phi I and phi j are both real. Now be careful, if phi I and phi j are both real, this particular guy is basically imaginary. The time translation invariance again implies that x tilde and x double tilde of phi I phi j depend only on t minus t dash. It's the time difference that depend on, not on particular times. So now we will discuss some of these analytical properties of the response functions. We are studying response functions, so we study their analytical properties. Now we have defined the function, we have made some changes to it to make it the mathematics more easy. Now we will study some analytic properties. So in order to keep the notation compact, now like we said, we are going to deal with equations which are very, very complex as we go ahead. So in order to keep the notation compact, we will consider that the response of a single position independent field to its conjugate external field. Be careful with the words here. The response of a single position independent field to its conjugate external field is what we'll consider. So in this case, we have this particular line. So the average of the delta of phi of t is given by this particular integral. Again, note, this is a t dash. This is not exactly t minus t dash. So x tilde of t here is 2 iota eta of t x double dash tilde of t. Now both phi of t is average and h of t are real, so that x double dash of tilde is pure imaginary. We will be interested in the response as a function of frequency rather than time. Now again, we said we want to remove the dependence on time, so that's what we're going for here. We therefore need to calculate the temporal Fourier transform of x tilde of t. Temporal Fourier transform. Temporal, keep the word in mind. Because of the causal step function that is pre-factored in x tilde of t, it is useful to introduce the Laplace transformation as a function of complex frequency z. This is a new term here, Laplace transformation. We're introducing it as a function of complex frequency z. This particular guy here. Now the function x tilde double dash of t is bounded as t tends to infinity. It does not go as long or as it wants. It's bounded because a disturbance at time t equals to 0 will only produce a finite change in x phi t at other times. Very important notice. This particular line is the reason why x double dash of t does not go to infinity, because the change produced or the disturbance at time t equals to 0 will only produce finite change in phi of t at other later times. Thus, so because t is positive in the above integral x of z, xz is analytic in the upper half z plane, where imaginary part of z is 0. Now be careful with the notations. It's complex variables and it's gonna be involving geometry, so we have to be a bit more careful here. The function, I'll repeat it for comfort. The function x double dash of t is bounded as t tends to infinity because a disturbance at time t equals to 0 can only produce finite change at later times in the function phi of t. So we see that because t was positive in the above integral, xz is analytic in the upper half z plane. Z plane basically is this guy z, so imaginary part of z is greater than 0. It cannot go down. Basically this is the complex plane, right? So the complex numbers are here and the real part is here. So this is positive and this is negative. That's what we're doing here. Now the function x double dash of t comma t dash is the same as x double dash of t minus t dash. This particular function is bounded and we can define its Fourier transform. Now note, it's bounded, so we're defining its Fourier transform with respect to a real frequency variable as given by these two equations. We've defined it with respect to a real frequency variable. If x double dash of t approaches a constant at t tends to infinity, if x double dash of t, which was by the way bounded, will approach some constant as t tends to infinity, then x double dash of omega will have delta function paths. Note, delta function paths. So now what happens is, so we discussed some general arguments in section 7.6. It's not right here, so we'll have to go to the other sections for that. We're not doing that right now. But we realize that x double dash of t is minus x double dash of minus t. This usually makes it an odd function. This, along with the fact that x double dash of t is pure imaginary, implies that x double dash of omega is real and odd. Again, we assume this would be, that's how it's turned out. It's an odd function in omega. So equation 7.1.12, which we did over here, this guy here, and then 7.1.5 and 7.1.16 imply that xz will be given as the integral from 0 to infinity of this guy and minus infinity to infinity of this guy. Turns out we have to do a bit of a mathematics. We open and we transform variables, and then we come to this particular state. The pi and the 2 can be moved out straight away. You do a bit of an integral with respect to omega, and then you shift terms around, and then you get the last integral. Now, this representation of x of z, I'm saying it x of z, it's a different symbol, but let's say it's x of z for now because there's no other x of z, so just keep it simple. This representation of xz shows clearly that it only has singularities on the real axis. Now be careful here. Singularities usually would mean this guy is going on for 0, something on those lines. It has only on the real axis and is therefore analytic in the upper half plane. It's analytic in the upper half plane. The time dependence response functions x tilde of t is the inverse Laplacian transform of xz, which in the present case is an integral along a contour in the upper half plane. It's an integral along a contour in the upper half plane. Be careful of these equations. Now in this equation, it's given an integral with minus infinity plus iota c to infinity plus iota c. The jumping boundaries over here, where c is any real number. Basically, infinity goes to the real part and some iota c here and some minus iota c. So they're dealing in this particular range over here. So just be careful about that. Like we have to be mindful of that. Okay. So the result is most easily derived using equation 7.1.7. If t is bigger than 0, the contour can be closed in the lower half plane, and there's a contribution to the integral as z equals omega. If t is less than 0, the contour can be closed in the upper half plane. Note again, if t is bigger than 0, the contour is closed in the lower half plane. If it's less than 0, the contour is closed in the upper half plane. Thus, x tilde of z is 0 for t less than 0 and is equal to 2 iota x double dash of t for t bigger than 0. Now, the response function x of omega relating the average delta of phi of omega to delta of h of omega can be obtained by using the Fourier representation, which is this guy. So, eta of t is limit as e tends to 0, going from minus infinity to infinity for d omega. Now, we obtained this response function by using the Fourier representation for the step function. From this, and equation 7.1.14, which is this one, we obtain this particular average. So this integral is what we are solving, and we end up with x omega and delta of h of omega, where x of omega is limit as e tends to 0, x of omega plus iota e. Iota e was basically tending to 0 in the above integral here. Now it's being used again with it's tending to 0. So the more we come close to the real value, the more we approach the actual x of omega, where x of omega plus iota e is given by equation 7.1.17, which is this guy, where with z equals to omega plus iota e. Thus, so what we see is that the response function x of omega is the limit as z approaches the real axis of the function x of z. Real axis, because see, as iota e goes to 0, omega goes to real, and what is z? Omega plus iota e. So as e goes to 0, z approaches omega. So as the imaginary part goes to 0, it approaches the real axis. That's what they're saying here. Z approaches the real axis of the function xz, which is analytic in the upper half plane. So when the frequency of the external perturbation tends to 0, external perturbation, it's a very fancy name they're using for practically, which is noise, but it's okay, it's a formal name. So the frequency of the external perturbation tends to 0, x of omega must reduce to the static susceptibility, static susceptibility. The dynamic parts are gone now. This basically is what we call as a sum rule, which relates an integral over x double dash of omega to a static quantity, which is called, as the name would suggest, the static susceptibility. There's nothing surprising here, there's just naming around things. So because the static quantity is a thermodynamic derivative, they're all fancy terms here, but we have to be a little bit mindful of them. So thermodynamic derivative, this is often called the thermodynamic sum rule. Let's go over that part again. Lots of big words coming here. So the sum rule, what we arrived here is called the sum rule, relating an integral over x double dash of omega to a static quantity, which is called the static susceptibility. That part we did. So now because this static quantity is a thermodynamic derivative, this is called the thermodynamic sum rule. Because it's a thermodynamic derivative, we call it the thermodynamic sum rule. It is one of a hierarchy of sum rules, which we will discuss later in section 7.6. It will come at some later point in time. We probably won't be doing it unless it's at the very end of the paper. The function x of omega, which we arrived at somewhere around here, this guy, yeah. Unlike its static limit, has a real part and an imaginary part. Now this guy is mostly real because it has a limit. So e tends to 0, the whole thing tends to real. But it normally, unlike its static limit, has a real part and an imaginary part, which can be seen using the identity, this guy. It's a new identity we're getting here, where this particular symbol, this is here and here, it signifies a principal part. Now what's a principal part? I think it's the real part of the number, but I'm not entirely sure, so we'll reserve a judgment over that. So the result signifies the principal part in equation 7.1.7. Again, the principal part of this equation, and in 7.1.17 and 7.1.20. So in this part, so the principal part of those two equations is represented by P here. So the result is x omega is x dash of omega plus iota times x double dash of omega, where again x dash of omega is this principal part multiplied by the integral going from minus infinity to infinity for the frequencies, for the derivative of the frequency omega. Now since x double dash of omega was a real function, x dash of omega also will be a real function. Thus x dash of omega, now be careful, I think they're changing notations around here. X dash of omega and x double dash of omega, I'm calling both of them as x, but I think they might be different. Let's just keep our minds open here. Are respectively the real and imaginary parts of the complete response function x of omega. Looks like they were not, they're both the same x. So thus x dash of omega and x double dash of omega are respectively the real and imaginary parts of the complete response function. So equation 7.1.25, this guy, big integral over here, is also called the Kramer's chronic relation between the real and imaginary parts of x dash of x of omega. Let's go over this part again. There's a lot of maths that happened there. We'll go slowly and slowly, okay? So we arrived at x double dash of omega. We said that, okay, it's a real function. But now we realize x dash of omega will also be a real function. Thus, they both respectively are the real and imaginary parts of the complete response function x of omega. Now, what you notice is that why they're saying all this, it's because this guy here. So if both of them were not imaginary, we could not assign that this as real and this as imaginary. We're only doing that because x dash of omega itself is a real number. X double dash of omega is also a real number. So we know that, okay, for x of omega, the imaginary part is only this guy here. That's what they're doing, nothing else. So this particular equation, this integral over here, is called the Kramer's chronic relation. Kramer's chronic relation between the real and imaginary parts of x of omega. We'll have to rub it a bit because it hides the text here. But yeah, you get the point. There's also a complementary expression relating x double dash of omega to minus x dash of omega. This is another expression. This is most easily, basically we derive it, we want to make it easy, so we derive it using the Cauchy representation for x of z. X of z is basically given as this particular round integral. This symbol here usually means a round integral. With the contour t, so we are going around the contour t and integrating around the boundaries. That's basically what this is. When the contour T is a semicircle, show that figure 7.1.1. This guy over here, this huge figure over here. We're talking about this figure over here. Little bit eraser I want. Okay. So this equation basically follows xz in the equation follows because xz is analytic in the upper half plane. We established that over here. Where is it? Where is it? Okay. Yeah, okay. So as we shall see in section 7.7, this is again a promise. We don't know if it comes or not. X z tends to 0 faster than 1 by z. So as z tends to infinity in most cases of interest. In our case, in this case, the integral in 7.1.26, this guy, which is basically the Cauchy representation, reduces to an integral along a line just above the real axis. That is from minus infinity plus iota e dash to infinity plus iota e dash. Just look at this, guys. So this is infinity iota e dash minus iota e dash. So just above the x-axis, just above these ranges over here. Draw it with a different pen, but yeah, these particular ranges, so just above the x-axis. It's a bit more complicated than I'm drawing it, but okay. So now we set z as omega plus iota e, and with e dash less than e, we take this condition, we obtain this particular equation. We are settling this in the above equations here. So we have to obtain this particular integral. Now we use equations 7.1.24 and 25, which is 7.24 and 25. These particular equations we use. And we obtain another integral for x double dash of w, x omega, sorry, I'm really sorry, it's x double dash of omega. Now because x dash of omega is real and the x double dash is imaginary, we could also have obtained this result simply by taking the imaginary part of this integral over here. Would have been easier now. Now the real part of this integral yields this equation only, basically. There's not much of a difference there, just yields it opposite out. And these two equations of 25, which was the real part of 7.1.27 and equation 7.1.28, they are the usual Kramer-Kronig relations, which is what we got here, the Kramer-Kronig relations. They're just circling back and they're deriving it using different methods. Now, they require slight modification of xz if it does not fall off more rapidly than 1 by z at infinity. Often it is easier to measure x double dash of omega, say over a sufficiently large frequency range. The real response of the function, the phi that we're calculating, it can be obtained via 7.1.25. This is getting a bit convoluted here, so we'll take it slowly. We'll not rush it. There's no hurry as such. Now, the above analysis of the response of a single scalar field applies without change to more general response functions. This was only for a single scalar field, and we don't need to change it. This will go as it is ahead, and it can be applied to more generic response functions. Thus, the Laplace transform of x tilde phi I phi j satisfies this particular equation. Now, following the equation 21 and 24, which we did here, so 21, this guy, and 24, this guy is coming again a lot, so just be careful of that. We have these particular equations, so we substitute the values here, and then we got these two particular equations, where x dash of phi I phi j is related to x double dash of phi I phi j by a Kramer-Kronig relation analogous to 7.1.25. In section 7.6, again some promise for ahead, we will show that x double dash of x dash and omega is real, provided phi I and phi j have the same sign under time reversal. And there are no external fields or other parameters that break time reversal symmetry. So in this case, in our case, x dash of phi I phi j is the real part of, and x double dash phi I phi j is the imaginary part of the complete response function x of phi I phi j. The zero frequency limit of 7.1.30 is this guy here, leads to the thermodynamic sum rule. Thermodynamic sum rule was the term that came right up there behind. This is the thermodynamic sum rule. The spatial Fourier transform in the zero wave number limit of this equation gives, as before, the usual static susceptibility. This is the main thermodynamic sum rule. And when we take the Fourier transform in the spatial method in the zero wave number limit of this equation with the zero wave number limit, when transformed under Fourier equation spatially, gives, like it did before, the usual static susceptibility. So now, what we have done is we have studied from the starting. We'll see we have studied the correlation functions, and we have done the response functions now. which was basically the math that we were talking about. This mathematics now, we're going to apply in our next cases, in the further upcoming cases, to the harmonic oscillators, harmonic motion and oscillators. We will be using these two and we will continue that now. Just give me 2 minutes. Okay. So what do we have here? So we'll get an overview of this and then we'll go to the details. So harmonic oscillator, we'll study the undamped oscillator. Then we'll go to the damped oscillator, which is kind of obvious. And then we'll study the response functions. Thereafter, we'll see the dissipation mechanisms, energy dissipation, which is basically, when we go into the damped oscillator. So there's dissipation of heat there. So that's what we'll study as section 4 of harmonic oscillator. Then later on, we'll go to the Langevin theory. So section 7.5. Remember, a lot of the mathematics above was to be continued in section 7.6 and 7. That hasn't arrived yet. So we'll go there. So now we'll go to section 7.5, which is the Langevin theory. We'll study this, go through this for a bit. We'll have some correlation functions for diffusion, mind you. Then we'll keep going, some other heading, short-term behavior, etc. More and more. That's it. So section 7.5. We are not going into section 7.6, which was the basis for a lot of mathematics in the above material. So we'll have to keep that as a black box. Now we'll go back up and we'll start the harmonic oscillator. Pardon this break. Basically, I needed the break because like my voice was tiring out. But yeah, that's what we'll start. Okay. Yeah, that's it. Okay, so now we'll start with the harmonic oscillator. Now, harmonic oscillation, you can remember either the pendulum or the spring motion. That's basically what the harmonic oscillators are, the harmonic oscillation motion is. We'll start with the undamped oscillator, which is basically the ideal case. It just works normal. You can go on forever if you wanted to. That's what we'll start. Now, the dynamical properties of condensed matter systems, they're not gas, they're not liquids, they're condensed matter systems. They're very often dominated by harmonic oscillator-like modes. They just go back and forth and back and forth. These modes can include sound waves in fluids, elastic waves, phonons in solids, spin waves in magnets. The information about the frequency and the damping of these models, information about the frequency and damping. Frequency is for the oscillation motion and damping is how it slows down. It is contained in both dynamical response and correlation functions. So in this particular section, we shall explore in detail the response function of a simple damped harmonic oscillator. Its properties generalize directly basically to any system with well-defined modes at finite frequency. Remember that, finite frequency, that will be important as we go ahead. So the Hamiltonian is basically the sum of potential energy and kinetic energy of an undamped oscillator of mass m and spring constant k. So this guy is a spring constant and this is the mass, basically just going back and forth, and we are assuming no gravity. It could be easily be a horizontal plane just because of the space I had to draw it this way, but yeah. So this is the potential energy because of the spring, and this comes by the mass, by the moving momentum of the box of mass m. So the equations of motion for the position xt and the momentum p of t are calculated by taking their Poisson brackets with Hamiltonian. Poisson brackets, that's a new mathematical equation. Now we're not going to go into the detail of how Poisson brackets work because that's a bit out of scope, and what we'll do instead is basically we'll include material along with the report for this reading material, which will contain details of how Poisson brackets work. For now, we will assume their function that we know as a black box, and we'll go ahead. So the momentum and position equations are calculated by taking their Poisson brackets with the Hamiltonian. So x dash is basically velocity, p dot is force, that's the first derivative of momentum. This is the notation for the Poisson bracket. This comes out to be p by m. And the momentum comes out to be minus kx. Now minus kx, we know that's basically the, we know that, okay, a string stretched by an amount x applies a force minus k, so the opposite side. That's something we know. Now the mode structure implied by these equations, is obtained by assuming that both xt and pt are proportional to e to power minus iota omega t and solving the resulting characteristic equation. Be careful, these equations, what they're saying is that these equations imply some mode structure which we don't know yet, but we will obtain it by assuming that both xt and p of t, xt is position and p is momentum, they are proportional to e to the power minus iota omega t, and solving the characteristic equation that we get after we assume that. So basically what we have here is the determinant of this matrix comes out to be minus omega square plus k by m, which we have to equate to 0. This will result in two solutions to this equation, which is plus minus root k by m. Those will be the frequencies for our mode structure. Each of these solutions correspond to a mode of the harmonic oscillator, which is fine, it makes sense. Note that there is one mode per degree of freedom. So x and p, 2 degrees of freedom, we have one mode per degree of freedom. So 2 in total. The time dependence of each degree of freedom is governed by a first order differential equation in time. First order differential equation in time. Thus, there is one mode per first order differential equation. What we had before was one mode per degree of freedom. Now the per degree of freedom depends on first order differential equation in time. So now what we have is one mode per first order differential equation in time. Thus, there is one mode. This property is quite general and will be encountered again in a study of hydrodynamics of conserved and broken symmetry variables. This I don't think we do it in this case, but okay. We had some diffusion mentioned, so maybe this comes there. The variables x of t and p of t have opposite signs under the operation of time reversal. X of t and p of t, momentum and x of t, that's the position. They have opposite signs under the operation of time reversal. That is, if we change the time from t to minus t, x of t remains an even function and p of t is an odd function. So the Hamiltonian equation, which is this guy over here, and its associated equations of motions, which is these two, are invariant under time reversal. They are invariant under time reversal. The equations of motion relate the time derivative of a variable with one sign under time reversal to the variable with the opposite sign. What happens here is x is either invariant or variant, and opposite to that is p. So the p was basically variant, it was an odd function. It relates that to this, which is an even function. Similarly, this x dot is an even function, relates to p by m. That way we have our functionings. Now these relations lead to the off-diagonal terms in the characteristic determinant. These relations lead to the off-diagonal terms in the characteristic determinant and to real and non-zero solutions to the characteristic equations. This property basically is quite general. Modes at non-zero real frequency invariably arise from the coupling of variables with opposite sign under time reversal via first order differential equations in time. X and P had opposite signs under time reversals in the equations that we had, which were the first order differential equations in time. X and P had different signs under time reversal. Modes at non-zero real frequency invariably arise from coupling of such variables. What are those variables? They are X and P. Why are we taking them? Why are we considering them? Because they had opposite sign under time reversal via first order differential equations in time. Now we have taken the trouble to discuss the undamped oscillator in terms of first order differential equations determined by the Poisson bracket relations with the Hamiltonian to point out features of such equations that will generalize to more complicated dynamical problems. The first order Poisson bracket relations can of course be converted into the second order differential equations of Newton's second law by substituting equation 7.2.2 into equation 7.2.3. Take a note here. 7.2.2 into 7.2.3. The result is x double dash plus omega naught square x is 0. The equations 7.2.2 and 7.2.3 are invariant under time reversal and predict modes with frequencies plus minus omega. This finishes our analysis of the undamped oscillator, which means the perfect oscillator without friction, etc., without dissipation of power or energy or heat or whatever. Now we shall move on to the damped oscillator. Just hope I'm recording this. Yeah, I'm recording this. Cool. The damped oscillator. To introduce damping in an intuitive way, it's not usually intuitive because heat dissipates, and sometimes with increase in speed or with increase in forces that can increase or decrease. That's not usually easy to calibrate or measure. So now we will take some assumptions to simplify our work. So to introduce damping in an intuitive way, we place the particle of mass m into a viscous fluid. Now that's basically the best way to introduce damping. Viscosity slows things down gradually, not like stop, gradually. Now, when in constant motion, a ball or a particle, whatever, it experiences a friction force which is proportional to its velocity at small velocities. At small velocities, with the increase in velocities, the friction will change. The function of the friction that is being applied will change. So at this moment, under small velocities, the force can be written as F viscous is proportional to V is negatively proportional to V, where alpha is the friction constant with units of mass by time. Alternatively, we can say that the velocity depends on the viscous force in the following fashion, where 1 by alpha is called the mobility. So higher the alpha, lower the mobility. Higher the alpha, more the friction force. Makes sense. For a sphere of radius A moving in a fluid, now before this we had an atom of mass and now we have a sphere of radius R. So sphere of radius A, so A instead of R, that's fine. Moving in a fluid with shear viscosity N, shear viscosity N, shear viscosity, fluids go up and down. It's given by the Stokes law, 6 pi eta A. We will discuss the meaning of shear viscosity in the next chapter, so basically not now. The viscosity eta has units of energy into time divided by volume, which is called poise, in order of eta n tau c t. In a fluid with number density eta n at temperature T. Here the average time between molecular collisions is tau c. So for the moment, both alpha and eta can be regarded as phenomenological factors. The viscous force law, this guy over here, is strictly speaking only valid for a time-dependent velocity, zero frequency. It's time-dependent. It must approach zero, as we shall see ahead, which we will not see because it's section 7.7, at frequencies greater than tau inverse. So what they're saying basically is that for frequencies bigger than this particular guy over here, it must approach zero. What must approach zero? The viscous force law. For low frequencies or for low masses with density is much larger than that of surrounding fluid. However, it is a very good approximation to the exact force and we will use it without further apology. Forces are not exact. There's a lot of conditions to be applied before we apply this particular viscous force, and that's what we're assuming. We're assuming low velocities. We're assuming that the ball is very much more dense than the liquid surrounding it. All those assumptions we're taking, and that's why we're using it. And under those assumptions, this is a pretty good approximation. In the presence of a viscous force and an external force F, so there's a driving force and there's a viscous force. Newton's equation for one-dimensional harmonic oscillator becomes x double dot plus omega naught square x plus gamma x dot equals to f by m, where gamma is alpha by m. The characteristic decay time gamma inverse equals to m upon 6 pi eta a. This is of the order m upon alpha eta naught tau ct. What was eta naught? It is a number density, and tau c was this guy over here, molecular collisions. Average order of time between molecular collisions. Now, if the average interparticle spacing d is this guy, number density, assuming 3D function here, so tau to the power minus 1 by 3. The free mean path mu tc, mu is the velocity and tau c is the distance between, is the time between any two molecular collisions. So that's the mean free path. Where m naught is the mass of a fluid particle are of the same order, then gamma inverse is this particular guy over here. Thus, for all but the most microscopic of particles, m is much bigger than m naught, and gamma inverse is much bigger than tau c. What we are saying is that the ball that we're dealing with will be much bigger than the atoms around it. It's a very complicated way of saying it, but it establishes it beyond any doubt. That's what we'll go with here. So the viscous force breaks time reversal invariance in 7.2.9. Viscous force breaks time reversal invariance. Any microscopic Hamiltonian and its associated equations of motion must be invariant under time reversal. That's very important. So in the present case, the microscopic Hamiltonian is that describing the harmonic oscillator and all of the degrees of freedom of the fluid in which it moves. The viscous force here describes the average effect on the harmonic oscillator of interactions. Average effect on the harmonic oscillator, average effect of what? Of the interactions with the many incoherent degrees of freedom in the fluid. In general, basically, any energy in the harmonic oscillator will tend to flow irreversibly, which means once it's gone, it's gone. It's basically like heat dissipation, will flow irreversibly into the many modes of the fluid. Basically, simply saying, we lose our energy when we're experiencing friction in water. This is reflected in the sign of the viscous force, which leads to the decay of x of t with time, kind of what we said just now. Irreversible flow of energy into the incoherent degrees of freedom is called dissipation. We will look at this ahead. And F vis is a dissipative force. We will return in section 7.5, etc. We never do that. Oh, we actually will. 7.5 is there. To description of the harmonic oscillator when it is in thermal equilibrium with the fluids that it receives energy from, as well as transmit energy to the fluid. So now what we did was we are assuming that the ball is losing energy to the fluid. There can be cases the heat temperatures can be out of balance, so that both ways exchange of heat can happen. So we have to be very careful of that. Now the mode structure of the damped harmonic oscillator is determined by the equation this one. Mode structure of the damped harmonic oscillator. The mode structure of the undamped was with two equations. For the damped oscillator, it's with this guy, with solutions given by plus minus omega 1 minus iota gamma by 2. Gamma is this guy over here. Gamma is this guy here. Just erase it so that it's particularly visible, but gamma is this guy over here. Now, if omega naught square is bigger than gamma square by 4, this guy, omega naught square, gamma square by 4, then omega 1 is real. And the solutions for x of t will oscillate with frequency omega 1 and decay in time with time constant tau equals to 2 by gamma. However, if it's less than that, see, the thing is, this is a square root, so it cannot be less than other unless it's imaginary. If it's bigger than that, only then it's real. Otherwise, it's not real. If that happens, omega 1 is imaginary and there will be no oscillatory component to x of t. There will be no oscillatory component. Omega is imaginary. It's literally imaginary. That's what the math says. In this case, the oscillator is said to be overdamped with inverse decay time. So there is no concept of any increase in velocity. It will just go down. Overdamped. It's just inverse in the decay time. Now, when gamma naught square is much less than gamma square by 4 now, it's not just less, it's much less. The fast decay time tau f is much shorter than the slow decay time. Thus, for times long compared to tau f, the first mode can be neglected. It will just go to 0 like that. This corresponds in the original equations of motion to neglecting the inertial term mx bar. Now the dots are joining. The resulting equation of motion is exactly what we had before. Thus, this appropriate equation of motion is often written as minus kappa by alpha x plus 1 by alpha f, which is minus, let's say, tau del by del x of the Hamiltonian into time, or t. Let's just call it t. Let's not call it time. Let's not call it time. It's only t. Now, what was tau? It was alpha inverse. What was h of t? It's h minus f of x. That is the total Hamiltonian, including h external. This is very useful, very useful in describing the dynamics of system, such as polymers in solution. Polymers in solutions. Now we have to be careful, right? So the motion is not perfect. Some omega can be imaginary. Those motions usually don't happen in ideal conditions. They happen in real life conditions where we're dealing with polymers, etc. That's where those systems can be described using these equations. That's where it becomes really useful. Now we shall come to the response function. So I'm shifting my screen here so that I can see the number of pages left. It's getting delayed with time. So the response function. Now the frequency dependent response of x, frequency dependent response of x to an external force is easily calculated by using equations 7.1.20 and 7.2.9. 7.2.9 is right here, 7.1.20 I don't, it's way up there, 7.1.20. This guy over here, 7.1.1.20. We're not going back to it yet, so we'll just stick to our equations. So x of omega then comes out to be, again, so just be careful that I'm calling both of them x, it's not correct, but just doing it for ease of it. These two are not the same, they're different quantities, so just be careful there. Let's say capital X, okay, let's just call it capital X. So capital X of omega is equals to x upon omega, x of omega divided by f of omega, which comes out to be 1 by m into 1 upon minus omega square plus omega naught square minus omega into gamma. There's no particular joy in saying the mathematical part, so I'll just go to the explanation. So the denominator of this equation is precisely the characteristic equation determining the mode structure. We had a different one for the undamped one, we're having a different one now for the damped one. Thus, there are poles in capital X of omega at complex mode frequencies of the oscillator. There are poles in capital X of omega at complex mode frequencies of the oscillator. This result is quite general. So, a static external force F, static external force F will lead to an equilibrium displacement of x equals to F by K. Kind of obvious. And this result is correctly described by the zero frequency limit of equation 7.2.16. Which is limit omega tends to 0 x of omega, basically limit omega tends to 0 x of omega, capital X of omega gives 1 by m omega naught square. This goes to 0, this goes to 0, this is omega naught square, which is 1 by k, which is del x by del f, which basically is capital X. Now at high frequency, capital X of omega is negative and falls off as omega negative square with a coefficient that depends only on the mass, this guy. What they're saying is if this guy goes up exponentially, we can basically just ignore the other two. You know, omega naught square will actually be quite over and up, above, up and above minus omega. So we do that. We ignore it. Now we will reconsider this result in section 7.6, which we're not going to do because this section is not part of the book. Now the imaginary part of the response function is, the imaginary part of the response function is x double dash of omega, which is slightly varying with this. Okay, so what happens in this guy is you take the derivative, what happens is minus 1 by this guy, derivative of this guy, then another minus 1 by this guy, derivative of that guy. So we just we have to differentiate that. It's a bit complicated, so we'll skip that for now. We arrive at this equation. We split this into partial fractions. A very, very important concept, usually very ignored, but yeah, it's extremely useful. So we get this particular partial fraction and we solve it, we take the limits and then we arrive at the final answer. Now we see from this that x double dash of omega is real and odd in omega, and it has peaks with Lorentzian line shapes. Another new term, Lorentzian line shapes, centered at omega equals to plus minus omega 1, where omega 1 is real, with half width at half maximum equal to gamma by 2. Just be careful. Furthermore, when the viscous damping is set to 0, so when the viscous damping is 0, there is no damping, then x double dash has a delta function spikes at frequencies plus minus omega naught of the undamped oscillator. This is so beautifully fits. It's almost perfect. The real part of the response function is x dash of omega is 1 by m omega naught square minus omega square. Yeah, you just say the math. There's nothing other than that. So x dash of omega is positive for omega less than omega naught. Omega less than omega naught, it becomes positive, tending to 1 by k as omega tends to 0. So if omega goes to 0, these both go to 0. It's omega naught square by omega naught power 4. Omega naught square by omega naught to the power 4, which is 1 by m omega square, which we get this, minus 1 obviously. And it is 0 exactly at omega is to omega naught. So when omega equals to omega naught, this guy and this guy both go to 0. So it becomes completely 0. X double dash of omega and x dash of omega followed in figure 7.2.1. So this guy over here. Perfect diagrams. It's great to watch. The symmetry fits out. The steady state time dependence of x of t in the presence of a force The steady state time dependence of x of t in the presence of a force is obtained from the real part of x omega f naught e to the power minus omega t is mod of x of w f naught e to the power minus t omega t minus phi. Just simplify that equation a bit because e to the power minus t can be cos of theta plus iota sin of theta. So that way we simplify it a bit and get this guy. Works out even. Now what we had was these response functions came out and the amplitude of x of t reaches a maximum for driving frequencies in the vicinity of natural frequency omega naught. X of t has an amplitude which reaches a maximum for driving frequencies that are in the vicinity of the natural frequency omega naught of the oscillator. Furthermore, the phase shift describing the degree to which x of t lags behind f of t and xt have a phase difference. That phase shift passes through pi by 2 at precisely omega naught. Now imagine that. It comes from the mathematics, so we are missing out on that because we're not discussing the maths in detail, but it just comes there. So they've written it, so we say that. Furthermore, the phase shift describing the degree to which xt lags behind ft passes through pi by 2 at precisely omega naught. Hence, mod of capital X of omega and phi of omega put in figure 7.2.2, which is here. In the overdamped case, the imaginary part of X of overdamped was when omega was imaginary, so remember that. In the overdamped case, the imaginary part of X of omega is peaked at the origin, rather than at non-zero frequencies. In the extreme overdamped limit at frequencies omega tf much less than 1 where the initial terms can be ignored, X of omega is this guy. And X double dash of omega upon omega is this particular sweet little thing over here. So what we get is X double dash by omega. It's a Lorentzian center. It's a Lorentzian center at the origin with a width tau s inverse as tau x. Let's just call it capital tau x. I don't know what the symbol is called. I'm really sorry. It is shown in figure 7.1.2.3. 7.2.3. Lorentzian center at the origin. So was it really this particular figure? But it was the Lorentzian. The high frequency behavior of x of z is determined by the frequency moments of x double dash of omega, as can be seen by expanding the integral representation of section 7.1.17. Section 7.1.17, it's way back, I'm going there. Now, I think it's the description of the diagram, so we could read it. Okay, fine, let's read it. Expanding the integral representation in powers of 1 by z. So powers of 1 by z. 1 by z integral representation. 1 by z square integral representation. Thus it goes ahead. So, I mean, we'll see it ahead. We don't see it now. We don't see it in the session. But if you read the book, you'll see ahead that x double dash of omega and x double dash xx of omega are actually quite proportionally related. We have the fluctuation dissipation theorem. Fluctuation dissipation theorem, another new term. To s of omega proportionate, I don't know what this term is called, so let's just go with it. Measuring fluctuations in x via x double dash omega of omega. Now the frequency moments of s of w are simply equal time correlation functions of x of t and its time derivatives. They are all finite. They're all finite. Just remember that part. That's important. Now the equation that we have here says that all moments of x double dash of omega by omega exist and are finite. The equation here says that all moments of x double dash of omega by omega exist and they are finite. The odd n moments are all zero because x double dash of omega is odd in w and hence they are all zero. The first two non-zero moments of the phenomenological form of x double dash of omega in equation 7.2.19 are finite. I'll repeat that part, it's a bit complicated. So the first two non-zero moments of the phenomenological form of x double dash of omega in equation 7.2.19, which we studied above, are finite. The zeroth moment in simply x, as required by the thermodynamic sum rule, we studied that above. The second moment is this guy. The zeroth moment was simply x. The second moment is this guy. Because, and it's equal to 1 by m because the average kinetic energy is T by 2. This agrees with equation 7.2.18. We did that above. It's coming back here again. This agrees with that equation and the high frequency expansion of 7.2.27. There is guy. The higher moments of equation 7.2.19 are infinite. They are infinite. So just we leave them here. We don't need them right now. The problem is that the phenomenological damping parameter gamma does not provide a correct description of the high frequency behavior. And that's a problem for us. That the damping parameter gamma does not provide a correct description of the high frequency behavior. In order for that all moments of x double dash of omega by omega to exist, gamma must be replaced by a function gamma of z, of complex z that tends to 0 more rapidly than any power of z. So the problem was that the phenomenological damping parameter gamma does not provide a correct description of the high frequency behavior. So we replace it with a function gamma of z. Instead of just gamma, we have gamma of z now. This complex z tends to 0 more rapidly than any power of z. So an often used phenomenological form of gamma is gamma of z, which equals to gamma of 1 minus iota z tau, where tau is the microscopic collision time. Now remember, tau c was the mean collision time. This is some microscopic collision time. So this form leads to a finite fourth moment of x double dash of omega by omega, but to infinite higher moments. It's a bit complicated. This entire section was quite complicated. So it's understandable if we don't have a complete thorough grasp of it, but we will attach material along with the report. So don't worry. But for now, let's just revise the last part that we did. The phenomenological damping parameter gamma did not provide a correct description of the high frequency behavior, so we replaced it with gamma of z, where the complex z tends to 0 faster than any power of z. That's how this function came about. And a very commonly used form of z is this function over here, where tau is the microscopic collision time. This particular form leads to a finite fourth moment of x double dash of omega by omega, but to infinite higher moments. Important parts over here. This is slightly complicated. It's okay if you don't understand it. We will attach material along with it. Don't worry. Now we shall study what's called dissipation. Okay, so we'll cover the concept of dissipation now. So what we've done so far is we've done undamped oscillators, we've done damped oscillators with frequencies that can be imaginary or real. We studied how the variations go, and then now finally we are coming to dissipation. Dissipation basically is how energy gets lost in a frictional medium by a box that's moving, or a ball of radius a that's moving. Okay, so we'll study dissipation now. So in steady state, we know that the external force does work on the oscillator, that is eventually dissipated as heat in the viscous fluid. That's fine. I'm sorry. The rate at which the force does its work is this guy, f of t into x dot of t. This is basically the velocity, but like it's varying with time, so we're saying x dot of t. Now, since in the steady state both f of t and x dash of t are periodic functions of t, with period t equals to 2 pi by omega, the average power dissipated is an integral over time t dt ft into x of t. Remember, fx is the work done. We are integrating that with time. So that's the power dissipated per unit time. This is the power dissipated per unit time. Just going to erase it to make it look a bit more prettier, but yeah, that's basically what's happening. What happens is, this is the power dissipated over time t, and this divided by time. So power is worked in per unit time. Now, using equation 7.2.21 for x of t, we obtain p equals x of t has an equation above. We substitute it here, and then get this part. So what we get is minus f naught square by 2 divided by time integral over time t dt of omega mod x of omega cos omega t sin omega t minus phi of omega. So you solve it and it comes out to be this particular guy over here in terms of x double dash of omega. Thus, we arrive at a very important result, basically, that the rate of energy dissipation is proportional to omega x double dash of omega. The rate of energy dissipation, that's the power dissipation, is proportional to omega x double dash of omega. The power is proportional to omega x double dash of omega. For this particular reason, that it's dependent, x double dash of omega is also sometimes referred to as dissipation. So we know that power is dependent on x double dash of omega. So sometimes we directly refer to x double dash of omega, saying that okay, power is dependent on it. So let's just call it dissipation. Now x double dash of omega is odd in omega. So w x double dash of omega becomes even. That means P becomes invariant to time reversal. We will see that ahead. So in thermodynamic equilibrium, oh my god, what is wrong with the mouse? So in thermodynamic equilibrium, the power dissipation must be positive always, implying that omega s double dash of omega must be positive. They can't both be negative, even then it will basically just be positive. So the positivity of omega s double dash of omega in the present case is associated with the positivity of the dissipative coefficient gamma. Dissipative coefficient gamma, take note. Dissipative coefficient gamma. It's, oh my god, what is wrong? What's this? What's this? So weird. Its sign was chosen so that the viscous force opposes motion of the oscillator mass. Its sign was chosen so that the viscous force opposes the motion of the oscillator mass. The sign is consistent with the energy transfer. The sign is consistent with the energy transfer from the mass to the incoherent degrees of freedom of the fluid and to positive power absorption. Now delta E, so I'm just checking. See, now one thing to note here, okay, this is page number, oh my god, this is page number 365. This is page number 381. We take a bit of a skip here, so it will not all be very apparent how this is happening, okay, but what we are working with is that the sign is consistent with the energy transfer to the incoherent degrees of freedom of the fluid and to positive power absorption. That's where we end. This section is from some other part which comes from here, which we have not studied. So now we'll just move on to the Langevin theory. Langevin theory. It talks about random forces and thermal equilibrium. Random forces can happen, but we need thermal equilibrium. So that's what we'll discuss now. This is where the harmonic oscillator discussion ends. We had undamped, we had damped, we had further sections in damped where we discussed dissipation, we discussed the response functions, we discussed the undamped oscillator, the damped oscillator, the response functions, and the power dissipations. We're done with that part now. So now we're going on to, now this part is something we're ignoring because it's coming from here, back here, which we have not done. See, page number 365 and page number 380. So we've made a bit of a jump here. Now we have what's called the Langevin theory. Now the erratic motion of the Brownian particle, remember Brownian motion? So that's water and everything moves around. So what we had was the erratic motion of, what is happening? I'm really sorry about this. I think some settings off. Yeah, see, something's off here. I'll try and be careful. Okay, so the erratic motion of a Brownian particle is due to collisions with molecules in the fluid in which it moves. These collisions, what happens is there's a collision and there's an exchange of energy between the fluid molecules. The temperature is T, and the Brownian particle. Now what happens is there's a lot of collisions that are happening. There's a temperature that's T, and ultimately what we want is thermal equilibrium between the various degrees of freedom. In a normal molecule, there's normally 6. So there's length, breadth, height, and then velocity has 3 components. So 6 degrees of freedom. Okay. This means that the mean square of each component of the velocity of the Brownian particle, mean square of each component of the velocity of the Brownian particle, average over a sufficiently long time. It keeps changing with time. So averaging over a long time must have the value T by M. T by M, that is the value of velocity that is normally assumed by the Boltzmann statistics. This average is maintained through constant collisions. Now, to understand how thermal equilibrium can be brought about by random forces, let us focus on a particle diffusing in one dimension. Now, individual molecules of the fluid, obviously they'll collide with this particle in a completely random fashion and exert a force whose time average is simply the viscous force. This is where our previous discussion comes to be useful. Air normally, in idealistic physics, we assume it's frictionless, but it has friction. This is called air resistance. It's less or more, we don't know, but for now, we'll assume it to be the viscous force minus alpha V. Okay. Now we can therefore break the force. Now we did this in before in the damped oscillator settings. Now we'll do it again with the air thing here. So we can break the force that is being put on the particle by the fluid, which is the air or the gaseous fluid or whatever, into two parts. The average viscous force alpha V and a random force tau of T. Again, we're calling it tau. I don't know what the symbol is called, so let's just call it tau for comfort purposes. Whose time average is 0. Now, the random force has a time average 0, but at any one point of time, there will be a certain random force. Now, this random force is well approximated by a sequence of independent impulses of random sign and magnitude. Random force. Okay, so random force, independent sign, magnitude, completely random impulses. Impulses, which basically we are calling that, okay, we're calling as a substitute for collisions. Collisions are also basically impulsive. They exert impulsive force. This is a stochastic process whose time average is 0. Ultimately, there's no real random force. Bunch of molecules stay where they are. Now, rather than considering averages over time, we will consider averages over the ensemble of possible random forces and represent the averages over this ensemble with brackets. In the same way that we represented averages over equilibrium thermodynamic ensembles. We will choose the ensemble of random forces so that averages over it are identical to averages over an equilibrium ensemble. We will choose these random forces or a bunch so that the averages over it are identical to the averages over an equilibrium ensemble. Thus, we have the average as 0. If each impulse is considered an independent random event, which we're doing, the probability distribution of tau of t is independent of tau of t dash for t not equals t dash. This implies the probability of it happening at one time is completely independent of probability of it happening at any other time. This implies that tau t into tau t dash averaged over average is called a delta t minus t dash is local in time. A is a constant that remains to be determined. We have not known it yet. Finally, tau of t in the independent impulse approximation. Tau of t in the independent impulse approximation is the sum of a large number of independent functions. The central limit theorem then implies that the probability distribution for t of tau is Gaussian. We assume it normally. Why? Because the more samples we have, the higher probability that we can sample using a Gaussian. That is basically what the central limit theorem is. Random forces are such as tau dash to give rise to erratic or noisy behavior of the observables and are often referred to as noise sources, especially in the context of electrical circuits, because this is happening in it also happens in electrical circuits, and that's what gives us noise. Now, equation 7.5.1 to 7.5.3, 7.5.1 to 7.5.3 provide a sufficiently precise characterization of the stochastic collision force. It's random, but we have a good, sufficiently precise characterization to allow us to discuss the establishment of thermal equilibrium. We know enough about this so-called random force to be able to work to establish thermal equilibrium. The detailed form of tau of t is determined by the temporal statistics of the molecules of the fluid. Thus, one expects the approximation of independent random events to break down. Thus, one expects the approximation of independent random events to break down for time differences less than a characteristic collision time t of the fluid. Take note here what they're saying. What they're saying is that we had an assumption which can break down if the time between two collisions is some, and we take a time less than that. As discussed in section 7.3, which I fear we did not do. There was no section 7.3. However, the characteristics time gamma inverse for motion of the Brownian particle is much larger than tau of t. And the independent collision approximation will be very good for times of interest. What they're saying is that the approximation can fail in certain cases, but for our case, it will work. Our Parameters are nice enough. The power spectrum of tau of t, or the Fourier transform average of tau of t dash, is given by I of omega is C. I don't know what the symbol is called, so let's just call it C dash dash omega equals to A. It's independent of omega in the independent collision approximation. A noise source with a frequency independent power spectrum is called a white noise source. A noise source with frequency independent power spectrum. Frequency independent power spectrum is called white noise source. So we have defined what white noise is. Now we'll study the correlation functions for diffusion. We had done Brownian motion. Now what we'll do is diffusion. So liquids have Brownian motion and liquids also have diffusion. So that's what we'll study now. We basically will show how knowledge of stats of the stochastic force, the random force, allows us to calculate correlation functions rather than response functions in the absence of external forces. The equation of motion of a diffusing particle is mv dot plus omega v is tau of t. Now the solution to this equation for v of t has a homogeneous part determined by the initial conditions and an inhomogeneous part proportional to tau of t. Now, since the homogeneous part, which depends on the initial condition, the homogeneous part of the velocity, which depends on the initial conditions, will decay to zero in the time of order omega inverse. The long time properties of v of t, the steady state properties of v of t, will be determined entirely by the inhomogeneous part and be independent of initial conditions. See, what's happening is in viscosity, there is an initial component, then there's stuff happening, and when steady state comes, the initial conditions become irrelevant. That's what we call as the steady state. In Fourier space, the inhomogeneous part of v is simply v of omega as tau of omega divided by minus iota omega n plus alpha. Now we use the equation 7.1.7, which we did long before, and 7.5.4, which is this guy over here. And we calculate CVV of omega, CVV, we did a correlation function right in the starting, so remember that, by averaging v of omega into v of minus omega over the random forces. Now CVV of omega is I of omega divided by modulus of minus omega m plus alpha whole square. Now the constant k that we got here characterizing the variance of the random force. Characterizing the variance of the random force is as yet unspecified. We don't know what is. We're just saying that okay, that can happen. Now we use this equation 7.5.7 to calculate the instantaneous mean square velocity in terms of A and thereby determine the value of A needed to ensure thermal equilibrium. What we're doing is we have the CVV of W as a function of A, that A is as yet unspecified, and that A characterizes the variance of the random force, and that is as yet unspecified. Now what happens is we will use this equation to calculate the instantaneous, which is at that particular time, mean square velocity in terms of this A, and thereby determine the value of A needed to ensure thermal equilibrium. We have the RHS, we need the LHS in terms of A, we will equate them, which will mean thermal equilibrium, and then we'll get the value of A. Now, average of V square is A by 2m alpha. In thermal equilibrium, V square is T by m. So we conclude A is 2 alpha T, which is 2m gamma T. 2m gamma T, which we have, if we substitute values from before, we get the average of tau T and tau T of dash as 2 alpha T delta of T minus T dash. Thus, the amplitude of white noise fluctuations is fixed by the requirements of thermal equilibrium. The thermal equilibrium will be there, the white noise will have to adjust. That's what they're saying, that's what we are saying, that's what everyone is saying. Now, the correlation function CVV of omega determines CVV of T comma T dash as the average of V of T VT dash, as well as the instantaneous average V square. Let's come again. The correlation function CVV of omega determines two things: CVV of T and T dash, as well as the average V dash V square average. Now, neglect of the homogeneous term in the solution for V of omega is only valid for times long compared to gamma inverse. Now, remember that steady state comes long after the initial state. So that time has to be there. The T has to be long enough and away, or actually much bigger than gamma inverse. Gamma inverse is the measure of time it takes to come to steady state. So if we take a long time after that, The Fourier transform of CVV of omega, I think I lost it again. One second. Yeah, go back. Neglect of the homogeneous term, it works for a long time, yes. So the Fourier transform of CVV of omega in equation 7.5.7, which is this. Therefore, gives the function CVV of t as limit tau tends to infinity, CVV of tau plus t comma tau. Now, CVV of t minus t dash then comes out to be integral of d omega by 2 pi e to the power minus omega t minus t dash into CVV of omega. That is t by m e to the power minus gamma mod of t minus t dash. This equation now shows that v of t and v of 0 become decorrelated for times larger than gamma inverse, which basically comes again and again to the fact that we are away from the steady state. And once that happens, once we are away from the steady state, the initial conditions don't matter. And that v of t, v of 0 average is of the order equal time thermal average t by m for times less than gamma inverse. Now the Fourier transform x omega of position is v of omega divided by minus I omega. The Fourier transform x omega of position is v of omega divided by minus iota omega. Thus, we can determine the position correlation function. Which comes out to be cxx of omega as 2 gamma t divided by m omega square into omega square plus gamma square. This comes from equation 7.5.7. That is again this guy right here. That's the equation we're using. Now the integral of cxx of omega over omega gives the mean square displacement x square of t. This integral is divergent, which means it will go above, it will shoot up very fast. Because the extra factor of omega square in the denominator of cxx of omega. And we correctly conclude that xt square is infinite. Slightly tricky to understand, but it's a very important thing. So this result that we just got, it is analogous to the result as we discussed in chapter 6, which apparently we do, I don't know, I haven't seen it. That the mean square of an elastic variable is infinite below its lower critical dimension. The average xt minus xt dash square is equivalent to delta xt minus t dash square. However, that average is finite. It's finite. So now we use this equation and the fact that the average is finite, and then we obtain this delta xt square as integral of d omega by t into 2cxx omega 1 minus e to the power minus iota omega t. This comes out to be, when we calculate the integral, we haven't done the technique part yet, but we substitute the value of cxx omega, convert that into partial fractions, and we get the answer as 4t by m omega integral of over d of omega of 1 by 2 pi 1 by omega square minus 1 by omega square plus gamma square into 1 minus e to the power minus omega iota t. Now the second term in this expression is easily evaluated by counter integration. Fair enough, counter integration. The first term, which is proportional to mod t, can be obtained from the second by taking the limits gamma tends to 0. Fair enough. Again, the result is this particular equation, where we use the Einstein relation d equals to d by t m omega. Now remember, Einstein's papers in 1905 were about three things: general theory of relativity, photoelectric effect, and Brownian motion. The Brownian motion is what we're talking about here. For times t much bigger than gamma inverse, this equation reduces to the result equation 7.4.11, which was predicted by the diffusion equation in one spatial dimension. Now, please take note, we have not done 7.4. It was not part of the materials, so we will not be explaining this. But 7.4.11 predicted by the diffusion equation in one spatial dimension. So at short times, now this was for long time. At short times, we get this particular equation, indicating that the Brownian particle moves ballistically in this limit. Now the Einstein relation can be re-expressed in various ways in terms of the velocity correlation function. The Einstein relation 7.4.26, we have not done that yet, by the way. can be re-expressed in various ways in terms of the velocity correlation function. First, we have the average of xt square as the average over integral of dt dash vt dash square over time t. We separate this out, calculate this part over here, and then arrive at the final answer, where the final expression in this equation can be obtained from the preceding line by integrating by parts. From this, we can easily calculate a time-dependent diffusion constant. Time-dependent diffusion constant. Fair enough. It's just simple maths. Now, what they're saying is that we calculated the time-dependent diffusion constant, which in the event of time infinite time limit approaches this particular guy. The last expression could have been obtained directly from equation 7.5.7 and 7.5.9, and the relation d equals to time by m, d by time, d equals to t by m omega. There's nothing very special in this. It's just simple maths playing around with it. Nothing much to explain as such. Now, we're going to talk about short-term behavior. Now, what we said was long-term. There is no link between the initial velocities and the steady state conditions. Now, we'll see the short-term behavior. In the above analysis, we argued that we could neglect initial conditions if we are interested in the long-term limits and thermal equilibrium. Initial conditions are, however, very often of interest and can be treated almost as easily as the long-term limits. The solution to equation 7.5.5 that came long back for V of t subject to the boundary condition that V of t equals to 0 is V naught, initial velocity basically is V naught, is V of t is V naught e to the power minus gamma t plus integral over time t. This is the solution for the velocity at time t, which is not very long. The average velocity thus is then V naught e to the power minus gamma t. From that, we get the velocity correlation function as V of t dash. We calculate this term and then we do these two integrals. We arrive at V naught square minus t by m e to the power minus gamma t plus t dash plus capital T by capital M e to the power minus gamma mod of t minus t dash. This is the velocity correlation. The velocity variance is delta V of t as t by m and 1 minus e to the power minus 2 gamma mod t. We're not going to do the maths in detail. We'll attach resources on the side. Now here we have used the equation 7.5.2 for the average of tau t and tau t dash with a equals to 2m omega t. Keep that in mind. These equations show that the velocity correlation function tends to the thermal equilibrium result of 7.5.10 for times t and or t dash much greater than decay time gamma inverse, regardless of initial velocity we know. Furthermore, if the initial velocity is averaged over an equilibrium Maxwell-Boltzmann distribution at time t, then Vt into Vt dash average has its thermal equilibrium form at all times. Interesting, all times. The displacement variable x of t can be obtained from the velocity by simple integration. Nothing special to be done here, simply Vt. Basically, yeah, Vt plus, yeah. Where, yeah, this is, now once we have x of t, we can calculate the average x of t. So there's again nothing really special there. It's just a bit of an integration being done. Similarly, we can calculate correlations in the displacement at different times t naught or t greater than 0, t dash greater than 0. Again, they're just playing with maths. There's nothing to explain as such. They're calculating three formulas. So what we got was basically velocity correlation, and the variance in velocity. Then we got displacement. Then we got the average displacement. Then we got displacement correlation, and finally velocity correlations. Now, using equation 7.5.20 for the velocity correlation functions, we obtain x of t minus x of t dash as in terms of velocity. So we have this in terms of velocity. We'll put those equations here and we'll get the final equations for this particular expression. If both t and t dash are much greater than gamma inverse, this reduces to the actual long-term form of our equations, and it is independent of the which we know. It's pretty straightforward from here on. If on the other hand they're very small, they're much less than that, then we get v naught square of t minus t dash ka whole square. That is, the Brownian particle moves ballistically with the specified initial velocity. Average over an equilibrium ensemble of initial velocities also reduces to 7.5.13. The average is obtained from 25, this guy, by setting t dash minus 0 so that t dash as 0 so that x3 dash equals to x0. First, finally, we can calculate the variance of the position. This is this guy. What we just did was this, basically this we are doing. We're just putting it here. Nothing really special. Just putting it here, yeah. What we did was we said t dash as 0, that's it. Now note that delta x of t is not equal to delta x t square, average of delta x t square. And that's because it explicitly retains the memory that initial emissions motion was ballistic rather than diffusive. They are not equal because there are mathematical factors which factor in the initial motion, and that way it becomes non-diffusive. There was Eastern Gaussian that still be taken into account. The variance does not, and is in fact, the variance does not be equal, and it's actually identical to delta x t minus t dash square average. The noise thought t is a Gaussian random variable. This we discussed before, and both v of t and x of t are linear functions of tau of t. Since linear functions of Gaussian random variables are also Gaussian random variables, the probability distribution functions for v of t and x of t are Gaussian. Since linear functions of Gaussian random variables are also Gaussian random variables, fair enough, the probability distributions for v of t and x of t are Gaussian and are completely determined by expectation values and variances of these variables. We leave a formal derivation of the results. So that's also what they are doing. That's what we'll do. Very close to finishing this off. So now we'll do the fluctuation dissipation theorem for the harmonic oscillator. We did the harmonic oscillator before. Now we'll do the fluctuation dissipation theorem. So a harmonic oscillator in a viscous fluid, like a free particle in the same fluid, it will reach thermal equilibrium as a result of collisions with the fluid molecules, etc. etc. This basically means that the average energy per degree of freedom of the oscillator will be t by 2, or that average of x square of t equals to t divided by m omega naught square, and v square of t average is t by m. We've done the math before, so we don't need to really go into that, so we'll go ahead. The equation of motion for an oscillator in a random force is given by the equation 7.2.9, with f replaced by tau of t. In the long time limit, we need only concern ourselves with the inhomogeneous solution. We know that already, right? We know that part. It's fine. Where x of omega blah, 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 blah. Now, the nature of the random force tau of t does not depend on whether our particle is attached to a spring of naught. It does not, it's true. The noise correlation function is thus independent of omega naught and has the same force form as for omega equals to 0. From this and the correlation function for tau of t, we obtain cx of omega as 2m omega t mod of x of omega square, which means 2 omega capital T by m 1 upon omega square minus omega naught square whole square plus omega square gamma square. We leave it as an exercise to verify that average of x square obtained by integrating this function over omega is in fact t by m omega naught square. We leave it as an exercise to verify that. Never mind. Then using equation 7.2.19 and the fact that average of x of t is 0, so that cx of omega equals to sx of omega, we obtain a very important result, which is x double dash of omega is half beta omega s double x of omega, where beta is proportional to 1 by t. This right here is the classical fluctuation dissipation theorem. The complete quantum mechanical version of this particular guy was originally derived by Callan and Belt in 1952, which is not of our concern right now. But basically what it does, it relates x double dash of omega, which we basically saw before. And it's proportional to the rate at which work done by external forces is dissipated as heat to the Fourier transform of the mean square fluctuation. We'll read again. It relates x guy of omega, which is something, to the Fourier transform of the mean square fluctuation. Thus, absorption or response experiments that probe this guy contain the same information as scattering or related measurements that probe this particular guy. Although we derived the fluctuation dissipation theorem for a single classical oscillator in equilibrium, although we derived the fluctuation dissipation theorem for a single classical operator in equilibrium in a viscous fluid, it doesn't matter because the theorem applies to all response and correlation functions of systems in equilibrium. Furthermore, it is applicable, as we shall see in the next section, to situations where the classical approximations are not applicable. It's a very tricky part to understand, but it's very straightforward once you read it again. We'll go through it again. So what we're doing is, this is the classical fluctuation dissipation theorem. This guy is the classical fluctuation dissipation theorem. The complete quantum mechanical version of this was originally derived by Callan and Welton, not of our concern, but it relates x double dash of omega to the Fourier transform of the mean square fluctuation. How that helps us is that it tells us that absorption or response experiments that prove x double x of omega contain the same information as scattering or related experiments that probe s double x of omega. Those two seemingly different things contain the same information. Now, although we derived the fluctuation dissipation theorem for a single classical oscillator in equilibrium in a viscous fluid, the theorem applies to all response and correlation functions of systems in equilibrium. What matters is equilibrium, not the other things. Finally, we come to the last section of our reading material, which is called the Fokker-Planck and Smoluchowski equations. Smoluchowski equations. It's a nice name. So in the preceding discussion, we focused on the correlation functions of velocity and position. The Langevin equations can be used to derive not only these correlation functions, but also the equations determining the entire probability distribution functions for these variables. The equation for the velocity probability function for a diffusing particle is called the Fokker-Planck equation. Coming in, the equation for the velocity probability function for a diffusing particle is called the Fokker-Planck equation. Its generalization to displacement and other variables, its generalization to displacement. Remember, it's a velocity probability function, but it can generalize, and its generalization to displacement and other variables is generally called Smoluchowski equation. These equations show, obviously, how probability distribution decays to Maxwell-Boltzmann distributions describing thermal equilibrium at long times. It's all coming together now. We have the times at smaller times, then we have Maxwell at smaller times, and then we see how one transitions to another. They are applicable not only for harmonic Hamiltonians, they are not only applicable for harmonic Hamiltonians, but also for anharmonic Hamiltonians, which contain other than the quadratic terms in the fundamental variables. This latter result that we just read is important because it implies that Langevin equations provide a correct phenomenological description of dynamics for all arbitrarily complicated interacting systems, as well as for simple free particles and harmonic oscillators we have considered so far. Let's go through this again. Why was the result important, and what result are we talking about? Is that the Fokker-Planck equations, when they generalize to displacement, etc., are called Smoluchowski equations. They show how probability distributions decay to Maxwell in long times, and they're applicable not only for harmonic Hamiltonians but also for anharmonic Hamiltonians. This is important because it implies that the Langevin equations provide a correct description for all arbitrarily complicated interacting systems, as well as for simple free particles and harmonic oscillator we have considered so far. So now we'll begin our derivation of Fokker-Planck equation by rewriting the equation of motion that we did before in terms of momentum p to produce a form that will most easily generalize to other variables. We said dp by dt is minus gamma p plus tau is minus capital tau del Hamiltonian by del p plus tau. We work on this mathematics, and the equation that we get is in a form that could in general include anharmonics in the Hamiltonian H. We wrote this in terms of H, and that can include anything it wants to include. So now we consider the probability P of P comma T given P naught comma T naught as average of delta of P minus Pt over P naught and T naught. We now consider the probability that a diffusing particle has a momentum P at time T. given that it had a momentum p naught at time t naught. The probability that a particle has this particular momentum at this particular time is given by p of p comma t plus delta t given p naught comma t naught as this particular integral. The conditional probability is called as average of delta of p minus p of t plus t dash delta t. This can be calculated by the equation of motion for p of t using this. The average of the third term in this equation is 0. Its square, however, is proportional to delta t. The terms which are higher in order than this particular integral are higher in order in delta t because tau of t is a Gaussian random variable, and averages of products of tau of t can be expressed as products of variance of average tau of t1, tau of t2. Thus, for example, average of integral of dt of tau of t to the power 4 approximates to average of d1 dt1 dt2 tau of t1 tau of t2 whole square, which further averages to delta t square. Short example. Using this result, we now expand the left hand side of equation 34 to the first order in delta t. Thus, and this is what we get for that. This particular result and the equation 32 then allow us to calculate del p by del t. It's a pretty neat answer for that. So the left hand side of this equation is 0 when p is approximately p equilibrium. That is, p has the equilibrium form which was given by Maxwell-Boltzmann statistics. In fact, p decays in time to p equilibrium. We are basically what we did was we studied equilibrium part, we studied the starting part, and we're seeing how the starting part decays to the equilibrium part. The probability distribution for any variable phi satisfying a linear differential equation in time of the form 30 will satisfy 38 with p replaced by phi. For example, the equation for an overdamped oscillator has exactly the same form of equation 7.5.30. The equation for p of xt, which is identical to 38 with p replaced by x, is the Smolov-Chomsky equation. What they are saying is that the velocities when replaced by distances are called the Smolov-Chomsky equation. That's what they did just now. The probability distribution appearing in the Fokker-Planck equation is for the momentum subject to the boundary conditions p of t equals to 0 is p naught. They are given the starting momentum as fixed. We have calculated both the expectation value p of t as given as m into v of t and the variance delta p of t as m square delta v of t of the momentum subject to this boundary condition. The force tau of t is a Gaussian random process governed by the probability distribution of 5.3. Since the velocity is linearly proportional to tau of t, it should also be a Gaussian random process. It should also be a Gaussian random process with a Gaussian probability distribution that is characterized only by its mean and variance. Now, one can easily verify after that that p of probability of a given momentum at a given time, given that a momentum at time 0 was p naught, is given by 1 by 2 pi delta p of t to the power half e to the power minus p minus average of p of t square divided by 2 delta p into t. This satisfies the Fokker-Planck equation. Now, this finishes our reading material 1. I'll wrap this up quickly. We studied correlation functions, response functions, and we did the same for the harmonic oscillators. We did the undamped, we did the damped, we studied their response, we studied their dissipation, and we did the Fokker-Planck equations and the Langevin equations for that. This wraps up our study material 1. We thanks a lot for this opportunity. We will submit this to the Moodle in a compressed file format, and all the reports and extra material that could be required for the mathematical portions will be attached alongside. Thank you very much. Good afternoon.